The covalent bond occurs when two atoms or elements with differences in electronegativity less than 1.67 form a bond or come together. And it has to do with the electron pair repulsion and proton pair repulsion fighting against each other, but the attraction of the nucleus of one atom for the valence electrons of another. In fact, the vast majority of compounds that you come across are covalent bonds. There are a couple different models to look at when it comes to the shape, structure, and properties of covalent bonds. The first one we're going to look at is the localized electron bonding model, or theory, which assumes that atoms bound together, or atoms in a covalent bond, are bound together by sharing electron pairs, and those electrons hold those two nuclei together. The electrons in the bond are called the bonding pairs, and the electrons not in a bond are the lone pairs. So for example, in ammonia, ammonia has a lone pair and 3 bonding pairs. You can also call lone pairs unshared pairs, and bonding pairs you can call shared pairs. Doesn't matter, it's just a matter of syntax and how you want to call them. The overall goal of a bond is to reach the lowest energy level. And the most stable and lowest energy level, or lowest configuration of an atom, is for an element to have 8 valence electrons. And since nitrogen is sharing a pair with hydrogen, nitrogen has 2, 4, 6, 8 valence electrons, and therefore is at its lowest energy configuration. Hydrogen's a bit of a freak and is happy with just having 2. So hydrogen has 2 and is at its lowest energy configuration in all 3 of these bonds. When a covalent bond forms, the very first bond formed, the first pair of electrons shared, is a sigma bond, denoted by the Greek letter sigma, which looks like an O with a tail over it, seen here. It is the strongest of bonds, at least for covalent bonds. The sigma bond will be the last bond to break because it's the last time. It's the bond of the pair of electrons that is found in the center of the electron orbitals, or wave formation. Every bond that forms after that, if it forms a double bond or a triple bond, here seen here is a double bond. A triple bond would have a pi bond, another bond that comes out of the screen, but we're just going to look at this double bond. Every bond that forms after the sigma bond, after the first bond, is a pi bond, and they overlap from side to side or top to bottom. Pi bonds are weaker than sigma bonds, but cannot exist alone. If you have a pi bond, you must have a sigma bond before that. So if I have a double bond, that means I have 1 sigma bond and 1 pi bond. If I have a triple bond, that means I have 1 sigma bond and 2 pi bonds. And there's no such thing as a quadruple bond, so we're done. Multiple bonds increase the electron density between the two nuclei, and therefore they decrease the nuclear repulsion, while enhancing the nucleus to electron density attraction. The nuclei move closer together and the bond length grows shorter for each type of bond. So a single bond is the furthest apart and therefore among the weakest. A double bond is stronger than a single bond, and a triple bond would be the strongest, because the nuclei have a very strong attraction for that very, very dense electron cloud between them. Multiple bonds, or double and single bonds, are most often formed between carbon, nitrogen, oxygen, phosphorus, and sulfur atoms, meaning a carbon and a carbon, or a carbon and a nitrogen, or a carbon and oxygen, or an oxygen and a sulfur. You get the gist. An atom with a lone pair, like ammonia, or a molecule with a lone pair, like ammonia, can form a coordinate covalent bond, where it can donate that lone pair, both of them, into making a bond with something else, which is what happens when ammonia becomes ammonium. another hydrogen, which is just a proton, accepts the lone pair from nitrogen, and they form a coordinate covalent bond. When one atom contributes both electrons, it forms a coordinate covalent bond. The octet rule is that atoms are at their most stable, or at their lowest energy configuration, when they have an octet for their valence electrons, meaning they have 8 valence electrons. So either they have 8 pairs of electrons being shared, or they have a lone pair and 3 shared electrons, but they are most stable when they fulfill the octet rule. There are exceptions to this, however. For example, hydrogen is satisfied with only 2 valence electrons, so it will always be a terminal atom, meaning it will be the last in a series. And any element less than carbon will be satisfied with less than 8 valence electrons. For example, boron is satisfied with just having 6 valence electrons. Beryllium is satisfied with just having 4 valence electrons. Elements in the third period or higher have d orbitals, which can be filled with more than 4 valence pairs in certain compounds. And the number of bonds depends on a balance between the ability of the nucleus to attract electrons and the repulsion between those pairs. And very few stable compounds contain an odd number of valence electrons and therefore cannot obey the octet rule. And these are usually nitric oxides and variants of chlorate, such as chlorite. Drawing Lewis structures is the best way to predict a molecule shape, and we will be predicting molecule shapes in the following videos. So let's go over how you can predict their shape, or how you can draw a Lewis structure. First off, you need to know that hydrogen is always a terminal atom, and it's connected to at least a different element. It can never, unless it's connected to itself and you have hydrogen, the molecule, it will always be connected to the central atom or to something else. It cannot be a central atom. To start, you always start with the lowest electronegative atom, and that is your central atom in a molecule. It is literally pushed by electron repulsion into the center of the atom. So carbon is going to be my central atom. Next, we add up all the valence electrons for the molecule. So we look on the periodic table. Carbon is in group 14, or group 4A, and therefore has 4 valence electrons. Hydrogen is in the alkaline metals and therefore has 1 valence electron. 4 plus 4 means we have 8 valence electrons to play with. How many pairs is that? We take 8 and we divide by 2, and we find that we have 4 electron pairs. Next, we go ahead and add the terminal atoms. So hydrogen, we have 4 hydrogens around this carbon, so we can put them around this carbon. Connect them with bonds. Each one of those bonds represents 2 valence electrons, or a pair, so that's 1, 2, 3, 4. We've used up 4 pairs. 4 minus 4 is 0, so we have no electrons left. Check to make sure we've satisfied the octet rule for each one. Hydrogen is satisfied with 2, so each one of these hydrogens has a bond to it. That's 2 electrons, so hydrogen is satisfied. Carbon has 2, 4, 6, 8. Carbon is satisfied. We have satisfied the octet rule, so this is a valid Lewis structure. In the case of hydrogen fluoride, hydrogen is the least electronegative. However, it cannot be the central atom because it is always terminal. But in this case, we'll make an exception for it because there are only 2 elements. So we'll say hydrogen and fluorine, and we know that somehow they're going to go together. Hydrogen again has 1 valence electron. Fluorine has 7. 1 plus 7 is 8. So we have 8 electrons to play with. Divide by 2, we have 4 pairs we can use. We bind the hydrogen to the fluorine. That's one pair. We have 3 left. We can show them around. We take them and put them around the fluorine. That gives us 2, 4, 6, 8. Fluorine is satisfied. Hydrogen is satisfied. We have satisfied the octet rule. And just to double check our bases, we used 3, so we have no electron pairs left to pair up. Nitric oxide. Nitrogen is in group 5A, so it has 5 valence electrons. Oxygen is in the chalcogen, so it has 6 valence electrons. And it has a +1, so that means that we lost an electron. 5 plus 6 is 11, minus 1, we have 10 valence electrons to play with, which means we only have 5 pairs. The least electronegative atom or element is nitrogen. It's going to be bound to oxygen somehow. So let's go ahead and bind them. That means we've lost 1. So we have 4 pairs left. Remaining pairs go around the terminal atoms. So that's 1, 2, 3. That's 1, 2, 3. We use 3. Used up 3. We have 1 pair remaining. The remaining pair goes on the central atom if there's room, and there is. But now we look, and we have satisfied the octet rule for oxygen, 2, 4, 6, 8. However, nitrogen only has 4 valence electrons and is not satisfied. So we need to make some double bonds because nitrogen and oxygen both are in our acronym for how do I pronounce this? For synapse, and therefore they can form double or triple bonds. So we can form a double or triple bond here. So let's take one of these lone pairs and turn them into a bond. So we would be with NO. 2, 4, 6. Not enough on nitrogen still. So let's take another one and move it in. It gives us triple bond nitrogen to an oxygen, each one with a lone pair on the outside. 2, 4, 6, 8. 2, 4, 6, 8. Both have satisfied the octet rule, and we have made a valid Lewis structure. Now you'll notice that when I did this Lewis structure, I used lines to represent my lone pairs. In the previous Lewis structure, I used dots. Either is acceptable on the AP exam, but you must have those lone pairs. If it asks for a Lewis structure is incomplete if you do not have the lone pairs to go with it. I could not just write H bound to an F. That is not a valid Lewis structure.